right, so I want to talk about progress quiz 2.51, linked in today's agenda if you aren't joining us today. Yesterday we did 2.5. There were common mistakes that I saw, so I tried to have those conversations with each person yesterday, so we're trying to address those specifically today. So, like for this one, a car is moving at a constant velocity. I give you a distance of 82, and I give you, it starts out at 15 meters per second. I'll be honest, I was trying to be a little misleading with it starts at, okay? It's not wrong, it did start at 15 meters per second. However, what does constant velocity mean?
I and VF are the same.
Yeah, our initial and our final are going to be the same value. Our velocity is constant means our acceleration is zero. There's just different ways to say that. So even though, yes, it is true that it started at 15, it also is going to end at 15. Okay? So with that, equation number 3 is the suggestion from this yellow sheet. Okay, kind of working through. It was a 1D motion problem. It's in the x direction. It's moving down the road. It's going further away. Okay, it's in the x direction. Okay, it is moving with a constant velocity. Because it says constant velocity, it means acceleration is 0. Initial velocity and final velocity are the same. I would suggest using equation number 3. You can use equation number 5. Equation number 5 says delta x is equal to VI plus VF divided by 2. So it's 15 plus 15 divided by 2 is 15. Is what you did, and then it's times t. So what you just did is you averaged those two velocities, and you ended up with your velocity times your time, and you get kind of the same equation when you're setting it down. Okay, you could use equation number 5. Yesterday's, your velocities were negative 2.4 and negative 2.4 though. Okay, because the velocity was constant. So that's why I put that one there. Constant velocity means acceleration is 0. I changed the wording right at the end. I originally had this type, the car is moving with no acceleration, which would mean the exact same thing. It's not accelerating, which means the acceleration is 0. Number 2, the reason I put number 2 on here is yesterday it was not as clean as this one. And I think, yes, if we look at this, I hope most of you will see like, hey, that's 2 times x, that's 2x. I can't just smash 2x and 9 together. Those are unlike terms, right? That's what we say in algebra. Those are unlike terms. So the 9 and this 2x they are not 11x. This has got an x in it, this is not. These are unlike terms. Now yesterday's was a little messier. Yesterday's ended up being like, I don't remember, something is equal to 1,444. And then it was plus 2 times negative 0.5 times delta x. Like that's what that left side ended up being. I'm sorry, the right side was. So what this simplified to is like that. And this is negative 1 times delta x. This has got an x. This is not. These are unlike terms. And you could look at this different ways. Sometimes people will go and they'll say, well, it's like that, right? Because this is just change this positive to a negative and times everything by negative 1, and then we get that. Some people did that, some don't. But the common mistake yesterday, and I tried to talk to each of you about this, is you combine these unlike terms. You took this negative 1 and you put it there, but that's not okay. Okay? So just like you can't smash these two together. That's the reason I put that one on there. For number 3, the reason I put number 3 on is this idea of 4 meters. It's dropped. How long? It's a 1D motion problem. It's a free fall problem. Acceleration is negative g, negative 9.8 meters per second. It's a dropped problem, so therefore my initial velocity is 0. And a common mistake I saw yesterday is people were saying this was 4. But the baseball is going down 4 meters, so my delta y is a negative 4 meters. That's important because this negative 4 And sometimes yesterday people weren't putting the negative next to the negative 9.8, but which way does gravity always cause things to accelerate? Down, right? Gravity's always pulling things downwards. Even if a ball is going up, which way is gravity pulling it? Downwards, and it's accelerating it downwards. So that's always going to be negative 9.8. Now, anytime you take the square root of a number, it's plus or minus. Same thing with this time. However, time always, in our examples, is always going to be a positive value. It's going to be a positive value. Okay. So let's talk problem types. Let me stop. Questions about any of these? Yesterday there was a fair amount of we made some mistakes, and that's okay, it's part of learning. Hopefully we learn from our mistakes, and that's why I tried to have that conversation with you. I know it took more time to get through those process problems. There was a lot of standing and waiting for Mr. Davies to get through them. I heard some conversations that were good about physics. I also heard some not physics conversations. But happened in the line too, like, oh, that's why that's a negative? Oh, okay, I get it. Right, so that's why that was, and then this hopefully is just to say, did we learn from that? Hopefully the answer was yes. Anything quick on this? Okay, let's take a look. We're gonna get this sheet out, the problem types, the if-then sheet. We're gonna add a problem type. We're going to add a problem type to our sheet. So, all right. So, new problem type. It's going to be a max height problem. Let's call it a max height problem. The reason is, when we throw this ball up, it reaches. Exactly. So it goes to maximum height and then it comes back down. It goes to maximum height and it comes back down. So the nice thing about max height is we can break a problem down and we can say, well, I know something about this ball's motion at its maximum height. So at its highest point, describe the motion of the ball right there. Right there. Right there. I can get fancy too. Woo! That was 2D, sorry. That was trying to show off. You guys can smile, because I'm trying to be silly for you. What's true about the ball's motion? Right there. Right there.
Stops.
It stops, right? At maximum height, the velocity is 0. So right there, the velocity is 0. And at that point, we can then talk about the velocity of it. Hey, Anthony. So at maximum height, the velocity stops. Just for a moment. And then what happens right after that? Oop, that's not a max height problem. It starts to come back down. Why does it start to come back down? Because of gravity. Okay, gravity's going to pull it downwards. And gravity's going to keep pulling it downwards until something else acts on it. So when the object's moving through the air, what force is acting on that ball? Am I acting on it now? Okay, so when it's moving through the air, what force is acting on it?
Gravity.
And only gravity, right? So what kind of problem is that? It's a free fall problem. On the way up, is the only force acting on it gravity? Besides when it's in my hand. Once it leaves my hand, is that the only force acting on it? What about on the way back down? Is that the only force acting on it?
Yeah.
Yeah. So on the way down, is it a free fall problem?
Yeah.
On the way down, is the acceleration due to gravity negative 9.8 meters per second squared?
Yeah.
Yeah, it sure is. Okay? And what about at maximum height? What force, oh, actually we should take a step back. On the way down, it's a lot like a drop. Okay? And let's rewind a little bit. Okay? Forget about the max heights for a second. Okay? Forget about those for a second. I forgot to talk about it. If I take this ball and I drop it, what's the acceleration due to gravity? Negative 9.8 meters per second squared. Okay, and it's going to accelerate downwards. What was my initial velocity? 0. And about how long does it take to get down there? Just kind of estimate. I'm gonna say maybe more 1, okay? 1,001-ish, okay? Really ballpark. It takes about 1, okay? So if I drop it from this height, it takes about 1 second. The initial velocity was 0. My acceleration due to gravity is negative 9.8. Because was it a free fall problem? Sure was. Okay. Now, if I take this ball and I throw it down, once it leaves my hand, again, once it leaves my hand, what force is acting on the ball?
Gravity.
And only gravity, right? Is it a free fall problem? So what's the acceleration? Negative 9.8. What's the initial velocity?
Wait, I didn't.
Is this 0 or not 0? Let's go there. If I take this ball and I throw it, once it leaves my hand, right there. 0 or not 0? Not 0. Why? I had thrown it, past tense. Okay, so the initial velocity is not 0. Which one hits the ground first? This one? Or this one?
Second.
The second one. Why though? Same height, same acceleration.
Is it because you're applying force on it?
I had applied a force on it, but that's not what I'm talking about when it's in my hand. I'm only talking about once it left my hand and down.
Its initial velocity is different?
Absolutely. The initial velocity was different. And that's the only reason it hits the ground faster. Because it had initial velocity once it was a free fall problem. Okay? I forgot to mention that. It's still a free fall problem because I mentioned this the other day. Jedi mind powers, right? And I don't know if it's a mind power if I'm trying to move objects. Kinda. You think I'm funny. You think I'm funny. Some of you catch either my Jedi mind trick worked on you or actually know what I'm referencing, one of the two. Anyway, I don't remember where I was going with that. Oh yeah, once it leaves my hand, I'm not pushing on it anymore. So once it leaves my hand, even if I threw it really, 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 really hard, once it leaves my hand, it's now a free fall problem. Okay, just we're clear. Okay, back to max height. Max height. Okay. Whee! Whee! Okay, so what happens when we talk about max height problems is we can choose maximum height to be one of my locations. Because when we make that list of variables, what we're really doing is we're comparing two locations. We're saying what was my initial velocity right here compared to my final velocity here. And I say, well, how far did I go from there to here? I'm comparing two locations, right? I'm just comparing from there to there. I'm talking about velocities, I'm talking about displacements. I'm comparing two locations. So if I start talking about max height problems, I can choose, very conveniently, I can choose that right there, my max height, to be one of my locations. Because at maximum height, I know something to be true. And at maximum height, I know the velocity of that object is 0. Okay? So the second to last thing on this list, it's a max height problem. And I know it's a max height problem because it says at max height, or it goes to its highest point. There's some different ways that we could word that. But at maximum height, we can say the velocity is 0. We can choose that location to be one of my two, and then that velocity would be 0. Now you have to figure it out. Is that your initial velocity, or is that your final velocity? And it depends upon the situation we're talking about. If we're talking about me taking a ball, and me taking a ball and throwing it from here to there, and it comes back to here, I might talk about the ball's motion from here to here. I don't know who it is. Oh, wait, voicemail. So the idea is, if I'm talking about the ball from here to here, I throw it from, leaves my hand, goes maximum height, then this is my starting location, this is my ending location. We then say my final velocity is 0, because at maximum height, that is my final velocity. But what also can happen is I can say I take the ball, I throw it from here to here, and then it comes back down. And if I'm talking about from maximum height back to here, at maximum height the velocity was 0, but now if I'm comparing this to this on the way down, this is my initial. So we have to kind of choose the location, and we choose it and we have to figure out, is it initial velocity or is it a final velocity? Okay, we have to kind of figure that out. Now, almost every time in my life, when I've taken an object and I've thrown it straight up, it's come straight back down. Almost every time. There's been a few times as a kid I'd throw like a ball up into a tree and it gets stuck. And then one time, it was one of the best days of my life. Besides, honey, when I married you and I had our children were born. Besides those special days, it was one of my, my wife probably watches my YouTube channel. I mean, why wouldn't you want to watch these, right?
She's supportive.
Yeah, I would watch her teaching 7th grade language arts if she posted her videos every day. Yeah, okay. But, so I had this water molecule. You remember these water molecules from biology class? They're magnetic? Yeah. One day I didn't have a tennis ball. So this is like, throw a ball and tree, get stuck. And then one time I was going like this because this is all I had. And it could never be replicated again. But I threw it ever just the right speed, and it stuck to the metal ceiling track, and it didn't come back down. It was amazing. But it's never gonna, don't say never, probably won't happen again. And it stuck, and it stayed there, and I left it there for like 2 years because I was so like happy at that moment. And then they redid the ceiling, and it came down. And I was sad, but it was still a great day. So besides that, at maximum height, what's the only force acting on that object? Except for when the magnet sticks, because that's another force now. Gravity. Okay? So, what's the velocity at maximum height? 0. What force is acting on that object at maximum height? Is there any other forces acting on that object? Okay, so if the velocity at max height is 0, what's the acceleration at max height? It's one of those two. It's either 0 or negative 9.8 meters per second. And the answer is negative 9.8 meters per second. And 0 is a very, very, very common one. I want to talk about this now to try to get it out of your head. If the only force acting on an object is gravity, then the acceleration is down negative 9.8 meters per second squared on Earth, right? Now let's imagine for a moment. It's not, but what if it was? What if my acceleration at max height was 0? Let's think about this. So at maximum height, what's the velocity? 0. Now, forget about the max height. Right now, what's my velocity? 0. If my acceleration is 0, and my initial velocity is 0, what's my final velocity in 3 seconds? 0. How far did I move? Nowhere, right? So now let's go back to the max height problem. If, it's not, but if my velocity at max height is 0, and if, that part is true, but if at maximum height my acceleration is 0, when it stops, and if the acceleration was 0, what would happen to this tennis ball at max height? If my acceleration was 0 when the velocity was 0, it'd float there forever and never come back down, right? But what is true is gravity is acting on it, and it does cause it to accelerate. It is still a free fall problem. Therefore, at maximum height, it's still going to be negative 9.8 meters per second. Squared. 9.8 meters per second squared. All right, let's take a look at in-class problem, and I want to do problem number 10. And we'll see how this goes. In the interest of time, it was a 2-part question. And I changed it to be a 1-part question. Okay, so on in-class problem number 10, I crossed off the first question. So in-class problem number 10 reads, the puck pops out of the floor of a dome hockey game at a velocity of 1.7 meters per second and lands on the table. How high, notice I crossed off the first question, how high did the puck go? So if you are not familiar with dome hockey, that's understandable because I don't know if it's really a thing anymore, but it used to be in like the 80s and 90s. it's kind of like foosball. It looks something like this. So you have like these controllers, and then you have these hockey players that you like spin around, and you try to get a goal. But right out of the middle, right here, the puck would pop up, and then you can slide these guys forward and backwards, and they spin around. And a lot of times, they were red, white, and blue versus red and white. And this is in the 80s. You may want to guess why. What famous hockey game was red and white versus red, white, and blue? Miracle on Ice of 1980, I think it was 1980 Olympics of Russia versus USSR. So that's what a lot of these colors are. Great to know. I'm glad I know that, Mr. Davies. I am glad you know that too. Okay, so that's what dome hockey is. The idea is the puck pops out of the table and it comes back down, and I crossed off the first question. We're only going to look at how high did the puck go. So we go through and we read this problem for kind of the same clues that we had before. We have a velocity of 1.7 meters per second, and we get the how high did it go. Now it does tell us and it lands back on the table. That is an important bit of information. But for this part right now, we're actually not going to use. Okay, so is this a 1D? We're kind of working through that problem set. Is this a 1D or 2D motion problem? Yeah, I guess that's the alternative. Is it a 1D motion problem? Yes or no?
Yeah.
Is it in the X direction or the Y direction? It's in the Y direction, okay. Which would mean then we make a list of variables with a delta Y. Is this puck moving at a constant velocity? No. Cross that off, right? No. Is this what's next? Is this a free fall problem? Is the only force acting on the hockey puck once it leaves the table gravity?
Yes.
Yes. Therefore, the acceleration is going to be negative g, which is equal to negative 9.8 meters per second squared because we're on Earth. Is the hockey puck dropped, or does it fall from the top of the game? No, it shot up out of a table. So this is not a dropped or a fall problem. Now we're at the, is this a max height problem? And the answer is it can be. It can be. Pictures are helpful. I'm going to draw my picture. I'm good. I'm going to draw my picture over here. So here's my amazing picture. There's my hockey puck. Here's my table. It pops out of the table at 1.7 meters per second. It goes up, it goes up, it goes up, it goes up, and then it, at maximum height, the velocity is 0 at its maximum height. Okay. At maximum height. Then what happens right after that? It comes back down and it hits the table going downwards. Now what's really going to happen is it's going to straight up and come straight back down, but I just didn't want to draw them over the top of one. Now, this is some type of velocity, 1.7. We have some velocity right here, and what we're trying to figure out is how high did this thing go? What I'm trying to figure out is how far is it from here, from the table, to that maximum height. Which variable does that represent?
Change in Y.
Change in Y. That's my delta Y is equal to my question mark. If I treat this as a max height problem, and I only look at from here to here, and if I only look at those locations, I was going to try to use a red marker, but I don't have any red markers anymore. So if I look at that and that only, and I realize this yellow, which is kind of a useless color, but if I look at max height and only to max height, I can set this problem up. And I can say this is my first location and this is my second location. So if this is my starting location, what kind of velocity would we title this? VI. And at maximum height, what would we call that velocity?
VF.
That'd be my VF. So then we can say my velocity is 1.7 meters per second, my initial velocity, and my final velocity at maximum height is 0 meters per second. And the question that we asked, is being asked, is how high did it go? I'm only looking at the upward part. I'm only looking at the upward part. So I'm choosing to only look at max height. I don't know time. I don't care about time. I don't know time. I don't care about time. So I choose an equation that doesn't have time, and that's equation number 4. And it looks something like that. My final velocity is 0, so my 0 squared is going to be 0. So what we end up with is 0 equals my initial velocity, which is 1.7, and it's going upwards. That is a positive 1.7. And then that's going to be plus 2 times negative a, which is negative 9.8 meters per second squared, times delta y. Zero is equal to 2.89 minus 19.6 times delta y. Algebraically, what do we want to do to get that next, to get that delta y by itself? Okay, so we really have 2 choices. Okay, and I heard add this to the other side, but remember we have to add this whole thing to the other side, right? Or what could we do to this piece?
Minus.
We could subtract it to the other side. I didn't hear it, at least I don't think I heard it. I didn't hear divide. We do not want to divide by 19.6 yet. Okay? So it's up to you. You can either subtract this or you can add this. It doesn't really make any difference. I'm going to subtract negative 2.8. I'm going to subtract 2.8 from both sides, and we end up with. Now, mathematically, we need to divide by. I think it's 14755 something 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 something. Okay. Now my general rule of thumb would be to round that to 0.15. Okay, but we'll just kind of leave it for right. Okay. I'm going to talk about this last piece without actually doing a calculation. What if I'm now going to look at from the puck and I'm going to look at it coming back down? Okay? So I'm now going to look at the downward part. I'm going to look at maximum height back down to the ground. And this is important, so hang in there. Okay? I'm now going to look at this hockey puck from maximum height, and it's going to be coming back down at some velocity. If I go through and I make my list, it's a 1D motion problem. It's in the y direction. What's the acceleration of this object at maximum height? Negative g, which is negative 9.8 meters per second squared. We said my initial velocity from max height coming back down is going to be 0. How far, what is the displacement of this hockey puck? It went from the table to maximum height. Now we're looking at maximum height back to the table. How far, what's my delta y of this hockey puck?
Negative 0.1.
It's going to be negative 0.147. What's the difference between this list of variables right, we solve for that. What's the difference between this list of variables and this list of variables right now?
The initial velocity.
The initial velocity is different, right? My final velocity is, my max height point is at a different location. Someone was going to make a prediction. Anybody want to predict what the final velocity of this hockey puck is going to be coming down?
1.7.
Yes,
Negative.
absolutely. It's going to be negative 1.7 meters per second. Because it's going to accelerate due to gravity, the same distance that it took to go up. What happens is these two get flipped. Now, what we can do, now if I were to have calculated the time, I didn't take the time to do this. Let's just pretend for a second this is 1 second. It's not, but let's just pretend for a second this is 1 second. If it took 1 second to get to max height, how long does it take to come back down? 1 second. What's the total time in the air then? 2 seconds, right? So our last problem type, and I do want to talk about this, is referred to as a delta y is equal to 0 problem. And a delta y is equal to 0 problem is when an object starts and ends at the same location. For example, I didn't go anywhere, right? You jumped really high, thank you. But I landed back on the floor, so technically I didn't move. I didn't, like, my displacement is 0. So we call it a delta y is equal to 0 problem. And a delta y is equal to 0 problem is when the object starts and ends at the same height. So sometimes, this is the very last line on your problem type. It's a delta y is equal to 0. Delta y equals 0. Delta y is equal to 0 when the object starts and ends at the same height. So in the problem we set up, this was not a delta y is equal to 0 problem, but it could be. Okay? The original question was, what's the total time in the air? We could have set it up as a delta y is equal to 0 problem. But if it's a delta y is equal to 0 problem, there's some things that we then know. We can say that my final velocity, and I know this is a little hard to read, it says my final velocity is equal to negative vi. It's going to come back in focus. And this is posted this will be posted on today's agenda as well. It's not there quite yet. It does say my final velocity is equal to negative vi. So it's the opposite. So here it was vi was 1.7. Now it's negative 1.7. Okay, it's the opposite. And if this says the total time is 2 times larger than the time to max height. Because sometimes we know the time it took to get to maximum height, or we've already calculated the time to get to max height. And if we know the time to get to max height or to come back down from max height, and it says, well, what's the total time? We can simply double that. Remind me tomorrow to talk about that sensor that they used to have, and I think they still have in gym, that measures your vertical jump. Okay, it's related to this. I'll post this in Canvas as well. Have a good day, everyone.